Welcome to our lecture on coastal and oceanic processes. Today, we will be exploring the powerful phenomenon of tsunamis, understanding their mechanisms and impacts, and then we will dive into the fascinating world of marine landforms, including the intricate structures of coral reefs. Let's get started. The word tsunami comes from Japanese, meaning harbor wave. A tsunami is a series of waves with very long wavelengths that occur in large bodies of water, like oceans. Unlike regular tides, they are not influenced by the gravitational pull of the moon or sun. Instead, they are triggered by massive disturbances that displace huge volumes of water. This can include megathrust earthquakes, violent volcanic eruptions, submarine landslides, or even meteorite impacts. Subduction zones, particularly around the Pacific Ocean, are notorious for generating these killer waves.
How exactly does a tsunami begin? It starts with a massive disturbance. In a megathrust earthquake, a subducting tectonic plate plunges beneath a less dense plate. Stresses build up until the locked zone abruptly gives way, thrusting the oceanic crust upward and vertically displacing a massive column of water. Other triggers include marine volcanic eruptions that create an impulsive force, submarine landslides where shifting sediments alter the sea level equilibrium, and even the rare but catastrophic impact of extraterrestrial objects.
Once the water is displaced, gravity tries to restore the sea surface to its flat shape, sending ripples racing outward. As these waves travel from deep to shallow coastal waters, they undergo a transformation known as the shoaling effect. The decreasing depth slows the wave down, but because the total energy remains constant, the wave's height or amplitude grows dramatically. Interestingly, the arrival of a tsunami is often preceded by a sudden, extraordinary recession of water from the shore, as the sea seems to draw a breath before the massive crests arrive in a series of waves. To understand tsunamis better, we need to review the basic properties of waves. The highest point is the crest, and the lowest is the trough. Wave height is the total vertical distance between the trough and the crest, while the amplitude is exactly half of that height. Wavelength measures the horizontal distance between two consecutive crests. The wave period is the time it takes for two successive crests to pass a specific point, and frequency is how many waves pass that point in a single second. In normal ocean dynamics, we see both horizontal motions, like currents and wind-generated waves, and vertical motions, like tides. In wind-generated waves, the actual water doesn't travel across the ocean. Rather, the energy, or the wave train, moves forward. The water particles themselves move in a circular motion, carrying objects up and forward, then down and back. As these normal waves approach the shallow beach, they slow down and eventually break when the water depth becomes less than half of their wavelength. When we compare normal waves to tsunamis, the scale is vastly different. Normal wind-generated waves have relatively short wavelengths of just a few meters to a couple of hundred meters, and periods lasting only 5 to 20 seconds. Tsunamis, however, are massive. They boast extraordinarily long wavelengths that can exceed 500 kilometers, and their wave periods can range anywhere from 10 minutes to 2 full hours between crests. Because the rate of energy loss in a wave is inversely related to its wavelength, tsunamis lose very little energy as they travel across entire oceans. While normal waves simply die out on the shore, tsunamis carry immense destructive energy inland. Furthermore, normal waves rarely exceed speeds of 60 kilometers per hour. Tsunamis, on the other hand, act like jet planes in the deep ocean, reaching speeds of over 350 kilometers per hour at a depth of 1,000 meters, and up to a staggering 850 kilometers per hour at depths of 6,000 meters.
Out in the deep ocean, a tsunami is virtually undetectable. A ship might ride over a tsunami wave and not even notice, because the wave's amplitude is tiny compared to its massive wavelength. But as the tsunami approaches shallow coastal waters, the front of the wave slows down while the back catches up. To conserve energy, the water is forced upward, drastically increasing the wave's height. In closed harbors or inlets, a funneling effect can occur, pushing these waves to terrifying heights of 20 to 30 meters above sea level.
Let's look at a devastating real-world example, the 2004 Indian Ocean tsunami. On December 26th, a massive 9.0 magnitude megathrust earthquake struck near the western coast of Sumatra. The Indian tectonic plate violently subducted beneath the Burma plate. This sudden movement displaced the ocean floor by 10 to 20 meters, tilting it downward. A huge mass of water rushed in to fill the gap, causing the ocean to withdraw dramatically from the coastlines of South and Southeast Asia before rushing back with catastrophic force. The waves generated by the 2004 earthquake traveled across the deep ocean at speeds around 800 kilometers per hour. As they approached landmasses like the Andaman Islands and Sri Lanka, the decreasing water depth caused their speed to drop below 70 kilometers per hour, while their height surged. The waves pushed up to 3 kilometers inland, causing immense destruction and claiming over 10,000 lives in India alone. Coastal regions were devastated, and Indira Point, the southernmost tip of India, was completely submerged by the rising waters. The sheer energy released by the 2004 earthquake and tsunami was so immense that it actually altered the geography of our planet. The violent shift in tectonic plates reduced the length of a day on Earth by 2.68 microseconds and shifted the North Pole by 2.5 centimeters. This slight change in the Earth's rotational velocity even impacted the Coriolis force, which plays a role in global weather patterns. Locally, the Andaman and Nicobar Islands were physically moved by about 1.25 meters. While we cannot predict earthquakes, we can detect tsunamis in time to issue warnings. Global systems aim to provide up to a 3-hour notice. The National Oceanic and Atmospheric Administration, or NOAA, established a system for the Pacific Rim back in 1965. They use DART gauges, which stands for Deep Ocean Assessment and Reporting of Tsunamis. These feature highly sensitive pressure recorders on the seafloor. When a tsunami passes, the pressure change is detected, sent to a surface buoy, relayed to a satellite, and analyzed by the Pacific Tsunami Warning Center in Hawaii to issue immediate alerts. Following the tragedy of 2004, India took significant steps to protect its coastlines. The Deep Ocean Assessment and Reporting System, or DORS, was established in the Indian Ocean. In 2007, the National Tsunami Early Warning Center was inaugurated at Inkois in Hyderabad. This advanced facility can detect earthquakes with a magnitude greater than 6.0 in the Indian Ocean and is capable of analyzing the seismic data within just 10 to 30 minutes, allowing for rapid evacuation orders. To ensure communities are prepared, UNESCO introduced the Tsunami Ready program, with tags awarded by the Intergovernmental Oceanographic Commission. In India, this is implemented by Inkois. Through its in-house Indian Tsunami Early Warning Center, it provides critical alerts not just for tsunamis, but also for storm surges and high waves. Recognizing its capabilities, UNESCO has designated this Indian center as a regional tsunami service provider, supplying vital warnings to neighboring countries across the Indian Ocean rim. Shifting our focus from oceanic waves to the coast, let's examine marine landforms created by wave action. First are blowholes, also known as spouting horns. These occur when a sea cave has a small opening at the top. As strong waves crash into the cave, they compress the trapped air. This immense pressure forces the water to burst upward through the hole, creating a spectacular geyser-like spout, accompanied by a loud, peculiar rushing noise. Over long periods, the relentless pounding of ocean waves can carve away coastal rocks, leaving behind a flat surface known as a plain of marine erosion. If this newly formed plain sits very close to the current sea level, other agents of weathering, like wind and rain, will continue to wear it down. Eventually, this transforms the area into a peneplain, which is a nearly flat, featureless land surface shaped by prolonged erosion. Not all marine landforms are created by erosion. Many are formed by deposition. The most familiar depositional landform is the beach. A beach is essentially a temporary accumulation of loose materials, such as sand, gravel, and rock debris. These sediments are continuously deposited and reworked by ocean waves and currents, resting upon a gently sloping wave-cut platform along the shoreline. As ocean currents and tidal forces move sediments, they often deposit sand and rock debris offshore, parallel to the coastline. When these ridges remain submerged underwater, they are called bars or sandbars. Sometimes a bar will completely enclose a body of water near the coast, creating a calm lagoon. If enough sediment accumulates so that the bar rises permanently above the water level, it becomes known as a barrier. Another interesting depositional feature is the tombolo. This occurs when a sandbar grows outward from the coast and connects the mainland to an island, or joins two islands together. We also have shoals, which are natural, submerged ridges or banks made of loose sand and sediment. Because shoals rise from the ocean floor to just below the water surface, they are notoriously dangerous hazards for navigating ships. When sediment is deposited in a long, narrow ridge attached to a headland at one end, while the other extends freely into the open sea, it forms a spit. If ocean currents cause the free end of the spit to curve back toward the land, it is called a hook. Finally, we have reefs. A reef is a ridge of rock or coral at or near the surface. The most famous natural reefs are built from the consolidated skeletons of corals, with the Great Barrier Reef in Australia being the largest on Earth, stretching over 2,300 kilometers.
Let's delve deeper into coral reefs. These vibrant underwater ecosystems are actually massive structures formed by the accumulation of calcareous skeletons left behind by dead coral polyps. Coral polyps are tiny, soft-bodied organisms related to jellyfish and sea anemones. They thrive in shallow, warm waters. To protect themselves, these polyps extract calcium salts from the seawater and secrete hard limestone skeletons. The diverse forms and brilliant colors of corals depend heavily on the specific salts they utilize.
Coral polyps do not live alone. They form massive colonies firmly attached to the rocky seafloor. As they grow, their tubular skeletons cement together into a solid rocky mass. When the living polyps die, they leave their hard skeletons behind, providing a perfect foundation for the next generation of polyps to grow upon. This cycle repeats continuously over millions of years, building up thick layers of limestone. Over time, these massive structures form coral reefs, and in some cases, they accumulate enough material to breach the surface and evolve into entire coral islands, like the Lakshadweep archipelago. Geologists and marine biologists classify coral reef structures into three major relief features based on their morphology and relationship to the land. These are fringing reefs, barrier reefs, and atolls. It is worth noting that classic circular coral islands are typically formed on top of atolls. Among these three distinct formations, the fringing reef is by far the most common type found in the world's oceans. Fringing reefs, also known as shore reefs, develop directly along the coastline, attached to the landmass. They are relatively narrow, usually only 1 to 2 kilometers wide. Between the actual beach and the main body of the reef, there is often a shallow, narrow lagoon. On the seaward edge, the reef slopes steeply down into the deep ocean. Coral polyps cannot grow further outward because the water suddenly becomes too deep and dark for them to survive. Excellent examples of fringing reefs can be found off the southern coast of Florida and the New Hebrides Islands. Moving further offshore, we find barrier reefs. These are extensive, linear reef systems that run parallel to the coastline. Unlike fringing reefs, barrier reefs are separated from the shore by a much wider and deeper lagoon. They often form a broken, irregular ring around a coastline or an oceanic island, acting as a massive natural breakwater. While they are incredibly famous, they are actually far less common globally than fringing reefs or atolls, which represent the next stage in the fascinating evolution of coral structures. Moving right into the cycle of erosion, we see that soil erosion is the fundamental loosening and displacement of topsoil. This can be a slow, natural geological process, or it can be rapidly accelerated by human activities like deforestation. When we look at weathering and erosion, they lead to two simultaneous processes: degradation, which is the mobile wearing down and transporting of material, and aggradation, which is the building up of material through deposition. The specific landforms created by this running water are what we call fluvial landforms. When rivers act as agents of erosion, they use several distinct mechanisms. Hydration is simply the sheer physical force of the running water wearing down the rock. Corrosion is a chemical process where the water dissolves the rock minerals. Then we have two physical processes that sound similar but are quite different. Attrition happens when the rocks and pebbles carried by the river crash into each other, breaking into smaller, smoother pieces. Abrasion, on the other hand, is when those rocks and pebbles are thrown against the riverbed and banks, grinding them down like sandpaper. The direction of the erosion drastically changes the shape of the river. Downcutting, or vertical erosion, digs into the base of the stream, making the valley deeper. Lateral erosion eats away at the walls of the stream, making the valley wider. Headward erosion is fascinating. It happens at the very origin of the stream, eating backward into the landscape and actually lengthening the river channel. Finally, we have braiding, which occurs when a river carrying a heavy sediment load on a low slope splits into a network of smaller, interwoven channels. As a river carves its valley, the shape of that valley evolves through different stages. In its youth stage, the river is highly energetic. The erosional action here is almost entirely vertical downcutting. Because the river is cutting down so fast, the valley walls don't have time to wear away laterally, resulting in a deep, narrow V-shaped profile with steep, convex slopes. In extreme cases, this intense vertical erosion creates massive gorges or canyons, like the famous Grand Canyon. As the cycle attains maturity, the river's energy profile changes. The steep vertical downcutting slows down, and lateral erosion, the wearing away of the stream's banks, takes over. This lateral movement causes the valley floor to flatten out and whiten. The steep wall-like sides of the youth stage gradually wear back into a concave slope. What was once a sharp V-shaped valley transforms into a broad, sweeping U-shaped valley.
Now let's look at the entire course of the river, starting near its source. Young rivers are incredibly dynamic. They are fast-flowing, high-energy environments where rapid headward erosion occurs, regardless of how hard the underlying rock is. Because the water is rushing down steep gradients, this is exactly where you will find dramatic features, like V-shaped valleys, turbulent rapids, and cascading waterfalls. The rivers originating high in the Himalayas are perfect examples of this youthful stage.
When the river leaves the mountains and enters the plains, it enters its mature stage. This is a lower energy system. Because the ground is flatter, the river starts to swing side to side, creating looping curves called meanders. The water moves faster on the outside of these bends, causing erosion, while it moves slower on the inside, causing deposition. You can see this beautifully illustrated by the rivers flowing through the vast, flat Indo-Gangetic Brahmaputra plain. Finally, as the river approaches its mouth at a sea or lake, it reaches old age. Here, the velocity slows to a crawl, and the river loses its ability to carry sediment. It drops this massive load, causing the river to become shallower and split into braided channels. This heavy deposition forms temporary river islands, like Majuli in Assam, the largest river island in the world. Ultimately, the sediment builds up so much that it extends the river's mouth out into the sea, forming a sprawling delta. Let's zoom in on those meanders. A meander is a pronounced curve in the river channel. The dynamics of the water flow create two very distinct banks. On the outer bend, the water is pushed outward by centrifugal force, moving faster and causing intensive erosion. This creates a steep vertical bank called the cliff slope side. Conversely, on the inner bend, the water is sluggish. It drops its sediment here, creating a gentle sloping bank known as the slip-off side. Usually, we associate meanders with soft, flat floodplains, but occasionally you will find deep, winding meanders carved directly into hard, solid rock. These are called incised or entrenched meanders. They typically form when a landscape is slowly uplifted by tectonic forces. The river, which was already meandering on a flat plain, suddenly gains a steeper gradient and starts vertically downcutting again, locking its meandering pattern deep into the bedrock. That sediment we mentioned being deposited on the inner slip-off side of a meander forms a specific feature called a point bar or meander bar. As the flowing water sweeps around the bend, it deposits sand, gravel, and pebbles in a linear fashion along the bank. These point bars grow gradually, building out into the channel. They are usually quite uniform in their width and profile, though they contain a chaotic mix of different sediment sizes. Over time, the continuous erosion on the outer bends of a meander makes the loop more and more extreme. The neck of land between the two sides of the loop gets narrower and narrower. Eventually, usually during a flood, the river simply breaks through that narrow neck to take the straighter, faster path. Deposition quickly seals off the ends of the abandoned loop, leaving behind a crescent-shaped, independent body of water called an oxbow lake. Over time, these lakes often fill with vegetation and turn into swamps. Sassinated, waterfalls are perhaps the most dramatic fluvial features. They are simply the fall of an enormous volume of water from a great height, almost exclusively found in the river's youth stage. They often form where a layer of hard, resistant rock sits on top of softer rock. The water erodes the soft rock underneath, creating an overhang that eventually collapses. The sheer impact of the falling water, along with boulders swirling at the base, carves out a deep, wide depression known as a plunge pool. To give you a sense of scale, let's look at some notable examples. In India, Kunchikal Falls in Karnataka is the highest at 455 meters, forming a stepped cascade. Nokkalakai Falls near Cherrapunji is India's tallest direct plunge waterfall. Globally, Angel Falls in Venezuela holds the record as the world's highest waterfall, dropping an astonishing 979 meters, followed closely by Tugela Falls in South Africa at 948 meters. Back in the rocky beds of the river valley, you might notice small, perfectly cylindrical depressions. These are called potholes. They are created by a fascinating mechanism called pothole drilling. When small fragments of rock get caught in swirling eddies of water, they start spinning in circles. Like a drill bit, these dancing stones grind down into the solid rock bed, carving out a small hole. As more stones get trapped in the hole, the drilling continues, and the pothole gradually enlarges. If you look at the sides of some river valleys, you'll see stepped benches that look like giant staircases. These are river terraces. They are actually the remnants of older, higher floodplains. When a river is rejuvenated, perhaps because the land uplifted or the sea level dropped, it starts downcutting again, carving a new, deeper valley into its old floodplain. The abandoned edges of that old floodplain are left high and dry as terraces. Pointing out, erosion isn't just restricted to permanent rivers. During heavy rainfall, especially in semi-arid areas with little vegetation, overland water flow concentrates into tiny channels called rills. As these rills flow downhill, they merge together, gaining volume and erosive power, eventually carving out deep, steep-sided trenches called gullies. Over time, extensive gully erosion can turn a landscape into a rugged, impassable badland, like the famous ravines of the Chambal Valley. If you let the cycle of fluvial erosion run its course over immense stretches of geologic time, it eventually wears the entire landscape down to an undulating, nearly featureless plain called a peneplain. The land is reduced almost to sea level, meaning the rivers have so little gradient left that essentially no more downward erosion can occur. The only things that stand out on a peneplain are isolated, highly resistant rock formations that survived the erosion, such as the iconic Uluru in Australia. We've covered how rivers tear down the land, but they are also master builders. Fluvial depositional landforms are created when rivers drop the material they've been carrying. This entire process is governed by stream velocity and the volume of the river load. Simply put, when a river slows down, it loses the kinetic energy needed to carry sediment. It is forced to drop its load, building new landforms in the process. One of the first depositional features you'll see occurs right at the foothills. When a steep mountain stream suddenly bursts out onto a flat plain, its gradient drops instantly. The water slows down and immediately dumps a massive pile of sediment. This material spreads out into a broad conical shape called an alluvial fan. Because the sediment blocks the original channel, the water constantly shifts its path, fanning out into multiple smaller channels called distributaries. Further downstream, the river builds its floodplain. This is the generally flat area stretching from the river's banks to the edges of the valley walls. The active floodplain is the riverbed itself, constantly being reworked. The inactive floodplain is the area above the normal banks that only gets covered during floods. When floodwaters spill over the banks, they lose speed and gently deposit fine silt and clay, creating incredibly fertile soils. Associated with those floodplains are natural levees. When a river floods and overtops its banks, the water velocity drops abruptly right at the edge of the channel. Because of this sudden drop in speed, the heaviest, coarsest sediments are deposited immediately along the banks. Over many floods, this builds up low, parallel ridges called natural levees. They act as natural embankments, keeping the river in its channel, but if a massive flood breaches them, it can cause catastrophic flooding in the lower adjacent plains. At the very end of its journey, the river meets the sea or a lake and forms a delta. This is a massive tract of alluvium built up at the river's mouth. Two things cause this massive deposition. First, the standing water of the sea acts as a wall, checking the river's speed and forcing it to drop its sand and silt. Second, a chemical reaction occurs where fine clay particles suspended in the fresh water coagulate upon hitting the salt water, clumping together and sinking to the bottom. Deltas come in several distinct shapes depending on the environment. The most classic is the arcuate or fan-shaped delta. This forms when the river deposits relatively light sediments, allowing the distributaries to easily shift back and forth across the mouth. This constant shifting distributes the sediment evenly, creating a smooth, curved, fan-like coastline. The deltas of the Nile, Ganga, and Indus rivers are perfect examples of this arcuate shape. A very different type is the bird's foot delta. Here, fine sediments, often rich in limestone, create impermeable banks that prevent water from seeping away. Instead of shifting laterally, the river is locked into a few main channels that push far out into the ocean, building long, narrow projections of land that look exactly like the toes of a bird's foot. This requires an environment with very weak ocean currents and tides, like the Gulf of Mexico, where the Mississippi River forms its famous bird's foot delta. Sometimes a river doesn't form a delta at all. If the sea level has risen and flooded the river valley, it forms an estuary. This is a submerged, funnel-shaped river mouth where fresh river water and salty ocean water mix. Because the river is dumping sediment into this deep, drowned valley, it forms mud bars and marshes rather than extending the coastline outward. Because they are deep and protected from harsh ocean waves, estuaries make ideal locations for major ports and industries, like the Hudson Estuary in New York. If a river empties into a sea with very strong wave action hitting the coast head-on, it forms a cuspate delta. Instead of spreading out, the strong waves constantly push the deposited sediment back toward the shore on both sides of the river mouth. This shapes the sediment into a sharp, pointed, tooth-like projection. Because the waves are so dominant, these deltas usually have only one main channel and no distributaries. The Tiber River in Italy is a classic example.
Geologists also classify deltas by what forces dominate them. High constructive deltas occur when the river's deposition completely overpowers the ocean's waves. These take two main forms based on water density. If the river water is lighter than the seawater, it flows far out on the surface before dropping its sediment, creating an elongate or birdfoot delta. But if the river water is dense and muddy, it mixes and drops its sediment immediately upon hitting the ocean, creating a rounded, bulging shape known as a lobate delta, like the Godavari. Conversely, we have high destructive deltas. In these environments, the ocean is the boss. The shoreline energy from waves and currents is so high that the sediment delivered by the river is immediately reworked and pushed around before it can settle. In these wave-dominated deltas, the ocean currents sweep the river's sand into long, arcuate barrier islands and beaches near the mouth, rather than letting the river build out into the sea. This constant reshaping of the land brings us to how these entire river networks are organized, which we will examine next when we look at drainage basins.
Let's begin by looking at the concept of a drainage basin, which is also commonly referred to as a drainage area, river basin, or water basin. You can think of a drainage basin as a giant funnel. It includes all the streams, rivers, and the surrounding land surface. Any precipitation that falls within this area is collected and channeled down to a single exit point. In some cases, we have what are known as closed or endoreic drainage basins. Instead of flowing out to an ocean, the water converges to a single point inside the basin, known as a sink. This sink could be a permanent lake, like the Dead Sea or the Aral Sea. It could also be a dry desert lake, such as Lake Chad in Africa, or even a point where surface water is lost underground, which is common with sinkholes in karst landscapes. Now, what separates one drainage basin from another? That would be a drainage divide. A drainage divide is typically a ridge or a high platform of land. In youthful, mountainous topography like the Himalayas, these divides are very conspicuous and easy to spot. However, in older, flatter landscapes, often called senile topography, like the rolling plateaus of the peninsular region, the divides are much less prominent and can be hard to identify. It is important to distinguish between a river basin, a watershed, and a catchment area. Both river basins and watersheds are areas of land that drain to a particular water body. However, a river basin is large and drains into a major river, while a watershed is a smaller area draining into a smaller stream or lake. Multiple watersheds make up a river basin. For example, the watersheds of the Yamuna, Chambal, and Gandak rivers all combine to form the massive drainage basin of the Ganga. Meanwhile, the catchment area simply refers to the total area that catches water, from rainfall, snowmelt, or springs, and directs it into the river. To give you a sense of scale, let's look at some of the world's most important drainage basins. The Amazon River in South America has the largest drainage basin in the world, covering over 6 million square kilometers and draining into the Atlantic Ocean. Other massive basins include the Hudson Bay in North America, the Congo River in Africa, and the endorreic basin of the Caspian Sea across Asia and Europe. Moving on to drainage systems, also known as river systems. These are the actual geometric patterns formed by the streams, rivers, and lakes within a drainage basin. These patterns don't just happen randomly. They are governed by tectonic irregularities, the nature of the underlying rock strata, and the gradient or slope of the land. Based on how the flow direction correlates with the local topology, we classify these patterns into two main categories: concordant drainage and discordant or insequent drainage. Let's start with concordant drainage. A drainage pattern is described as concordant if it perfectly correlates with the topology and geology of the area. In simple terms, the river's path is highly dependent on the natural slope and the shape of the land. This is the most common type of drainage pattern you'll find in nature. Concordant drainage is further classified into 4 types: consequent, subsequent, obsequent, and resequent rivers. The first type of concordant drainage is the consequent river. These are streams that follow the general direction of the initial slope of the land. Most of the rivers in peninsular India are consequent rivers. For instance, the Godavari, Krishna, and Kaveri rivers descend from the Western Ghats and flow naturally down the regional slope eastward into the Bay of Bengal. Next, we have subsequent rivers. After a main consequent river has been established, tributary streams may form by eroding headward along bands of weaker underlying rock. Because they follow these specific geological structures, subsequent rivers often meet the main stream at right angles. Good examples include the Chambal, Sindh, Ken, Bedwa, Tons, and Son rivers, which act as subsequent drainage by meeting the Yamuna and Ganga rivers at right angles. Once consequent and subsequent rivers have carved out their valleys, a third type can emerge, obsequent rivers. These streams flow in the exact opposite direction of the original consequent rivers' flow. They typically flow down the newly formed slopes of the river valleys and join the subsequent rivers at right angles. The final concordant type is the resequent river. A resequent river flows in the exact same direction as the initial consequent drainage. However, they originate at a much later stage in the landscape's evolution, hence the prefix re. They develop after significant erosion has lowered the landscape, but they still follow the original regional slope. Now, what happens when a river ignores the shape of the land? That brings us to discordant or insequent drainage patterns. A pattern is discordant if it does not correlate to the surface relief features or geology of the area. The river stubbornly follows its initial path, completely irrespective of changes in the topography around it. These rivers usually flow through highly sloping surfaces and are classified into two main types, antecedent and superimposed. Let's look at antecedent drainage. Imagine a river flowing across a landscape. Over millions of years, tectonic forces caused the land across the river's path to uplift. Instead of being diverted, the river has enough erosive power to cut vertically through the rising land like a saw, forming deep gorges. The river maintains its original course. The Indus, Sutlej, and Brahmaputra are classic antecedent rivers. They are actually older than the Himalayan mountains they cut through. The second discordant type is superimposed drainage. In this scenario, a river originally develops on a cover of softer rock. As it erodes downward, it eventually hits a completely different, harder rock structure buried beneath. Because the river already has an established path and high erosive power, it just keeps cutting downward into the hard rock, ignoring the new geological structures. The drainage pattern is essentially superimposed on the older buried rocks. Because the original cover rocks have completely disappeared due to denudation, the river's path seems to make no sense when you look at the current exposed bedrock. The river's direction relates entirely to a landscape that no longer exists. Excellent examples of superimposed drainage in India include the Damodar, the Subarnarekha, the Chambal, the Banas, and the rivers flowing across the Rewa Plateau. To summarize the difference, antecedent drainage cuts through a newly forming landform that is actively uplifting, like the Himalayas, often eroding through weaker sediments. Superimposed drainage, on the other hand, cuts deeper into an existing landform, uncovering buried, harder rock strata, like the rivers of peninsular India. In both cases, the river stubbornly maintains its original path. Now let's explore some specific geometric drainage patterns, starting with the dendritic or pinnate pattern. This looks exactly like the irregular branching of a tree. It develops in terrains that have uniform lithology, meaning the rock structure is consistent everywhere, and there are no significant faults or joints to guide the water. Because the rock erodes evenly, the streams branch out naturally. The Indus, Godavari, and Mahanadi rivers exhibit this pattern. Next is the trellis pattern. This looks like a garden trellis. Here, short subsequent streams meet the main stream at right angles. This happens in areas with alternating bands of hard and soft rock. The tributaries carve out valleys in the soft rock, running parallel to the hard rock ridges, before turning 90 degrees to join the mainstream. You can see this in the old folded mountains of the Chotanagpur Plateau and the Seine River Basin in France. In an angular drainage pattern, the tributaries join the mainstream at sharp, acute angles rather than right angles. This pattern is heavily influenced by the specific jointing and faulting of the underlying rocks, which dictate the angles at which the water can flow. This pattern is quite common in the foothill regions of the Himalayas.
The rectangular drainage pattern is exactly what it sounds like. Both the mainstream and its tributaries feature sharp right-angle bends, and the tributaries join the mainstream at right angles, creating a grid-like appearance. This occurs in regions where the bedrock is heavily faulted or fractured in a rectangular grid. The Colorado River in the USA and streams in India's Vindhyan Mountains are great examples.
When you have a central high point, like a dome or a volcanic cone, you get a radial drainage pattern. The streams originate at the summit and flow downwards and outwards in all directions, like the spokes of a wheel. A perfect example is the Amarkantak Mountain in India, where the Narmada, Son, and Mahanadi rivers all originate from the same high area, but flow out in completely different directions. A variation of the radial pattern is the annular drainage pattern. Imagine an eroded dome where alternating bands of hard and soft rock form concentric rings. The radial streams flowing down the dome develop tributaries that carve circular paths through the softer rock rings, wrapping around the summit. While not very common in India, it can be found in the Nilgiri Hills and around the Black Hills in South Dakota. In regions with a very pronounced uniform slope, we see a parallel drainage pattern. Because the slope is so steep and consistent, the streams don't have a chance to branch out much. Instead, they run swiftly downhill, parallel to one another. You can observe this with the small, fast-flowing rivers that originate in the Western Ghats and drop sharply into the Arabian Sea. The exact opposite of the radial pattern is the centripetal drainage pattern. Instead of flowing outward from a peak, the streams flow inward from surrounding high ground, converging from all sides into a central, low-lying basin or depression. This is the pattern that feeds those endorheic lakes we discussed earlier. You'll find this pattern in the high-altitude basins of Ladakh and Tibet. Sometimes there is no pattern at all. This is called a deranged drainage pattern. It is an uncoordinated, chaotic landscape of numerous small watercourses, lakes, and marshes. This is highly characteristic of regions that have been very recently vacated by a massive ice sheet or glacier. The ice scours the land, leaving behind irregular depressions that fill with water. We see this in the glaciated valleys of the Karakoram Range. Finally, we have the barbed drainage pattern. This is a fascinating anomaly where a tributary joins the main river at a backward angle, making it look like the tributary is trying to flow upstream. This usually happens due to a phenomenon called river capture, where tectonic tilting or erosion completely reverses the flow direction of the main river, but the old tributaries still point in their original direction. The Arun River in Nepal is a classic example of this. To wrap up our discussion on drainage systems, remember that drainage basins act as massive funnels for water, separated by elevated drainage divides. The rivers within them can be concordant, meaning they follow the natural slope and geology, or discordant, where they stubbornly cut through uplifting or buried rock structures. Ultimately, the geometric patterns these rivers form, whether dendritic, radial, or deranged, give us incredible clues about the underlying geology and the deep history of the landscape.